The final Doppler technology that we'll look at is Colour Doppler. This is obviously quite different to pulse Doppler and continuous wave Doppler in that its purpose is to produce an image of Doppler information rather than a measurement at a particular point or region. So the idea is that Colour Doppler produces a colour-coded Doppler shift image which is overlaid on top of the grayscale image. It's actually based on the pulse Doppler principle, but of course in Colour Doppler the machine is having to measure Doppler shift at hundreds or perhaps even thousands of points in order to produce a complete image. And it has to do that many times per second to provide real-time data. So essentially it has to operate very much more quickly than pulse Doppler. The way in which this is achieved is by taking a number of shortcuts, and I'll highlight this as I go through describing how Colour Doppler works. An important thing to keep in mind is that Colour Doppler is a qualitative modality. It's producing an image, and you can't really get accurate measurements from it. It is used for quantitative purposes in just one specialized area of echocardiography, but not otherwise. So this means that Colour Doppler is very much complementary to pulse Doppler with the spectral display. That's the technology that you use to get quantitative information. Colour Doppler gives you a different kind of information entirely. Here we have a Colour Doppler image produced with a linear array probe looking at the neck. So we have the jugular vein in blue and the common carotid artery in red. You'll notice that there are different shades of red. The blue looks rather more uniform, but there are variations in the red which indicate variations in the Doppler shift values. You'll notice the colour has only been acquired within the colour box, and so it's only within that region that the machine has to acquire Doppler shift information. The sides of the colour box slope, and this indicates the direction of the beam that was used to acquire the Doppler information. Remember, Colour Doppler is not acquiring quantitative information, so the exact angle is not important, and in fact it will vary as we're going to discuss later. On the left-hand side we have a colour bar which indicates how Doppler shift is converted into colour, and I'll talk about that more in a minute. So here's the general idea, that the beams are going to be parallel to the sides of the colour box. The very first beam is going to be running down the left-hand side of that colour box, and that's going to acquire Doppler information for that particular part of the colour box. It will then increment to the right, so the beam will be scanning in the direction I've shown with the arrow. And it will do that repeatedly, acquiring information starting at the left-hand side of the colour box and finishing up on the right-hand side. This highlights the fact that each of those beams is in fact acquiring Doppler information at many different depths, and so each beam has a large number of sample volumes. So this is one of the big differences between pulse Doppler and Colour Doppler. Colour Doppler uses many beams in different positions, and each beam has a very large number of sample volumes sampling the Doppler information at different depths. So there's a great amount of, much larger amount of data being acquired that has to be processed by the machine. The other thing that's shown here is that a very small number of transmit pulses are used for each position of the beam, and a typical number would be 8. So with the beam in one position, the machine will transmit and receive just 8 times, and it will then move on to the next position. And so that for any one sample volume, data from just 8 transmit pulses is going to be analysed to estimate the Doppler shift. Compare this with pulse Doppler with the spectral display, where information from approximately 128 successive transmit pulses is used to acquire the Doppler information. You can see an enormous difference. This is one of the biggest shortcuts, that in Colour Doppler, the number of pulses used to acquire the Doppler information for each point is very much smaller than it is for spectral pulse Doppler. So here's a timeline showing you what the transducer would see in an idealized sort of way. We have the transmit pulse, and then we have a series of range gates which are producing sample volumes spanning from the top of the color box down to the bottom of the color box. So the machine will be acquiring echo data from each of those range gates and processing each of them separately to produce Doppler estimates for each of the depths. Then, of course, the machine waits until it's okay for it to transmit again, and it transmits the next pulse and repeats that process. But remember, only around 8 times before it moves the beam to its next position and starts again. So let's look at how the machine processes that small amount of information that it has for each individual range gate. The information is first wall filtered, and then the machine calculates 3 numbers to represent the Doppler information for that particular sample volume. And these 3 numbers are listed here. The mean Doppler shift, so that's just the average Doppler shift for the blood flow within that sample volume. And secondly, the Doppler variance, which is a measure of how broad a range of Doppler shift frequencies there are at that particular time in that sample volume. So the variance is a measure of the width of the spectrum. And then the Doppler power, which is a measure, of course, of the strength of the Doppler signal. So all the machine has acquired for each sample volume is those 3 numbers: the mean Doppler shift, Doppler variance, and Doppler power. It looks at each of these parameters, and in addition it looks at the grayscale value at that same point, and with all of that information it makes a determination: is that point tissue or is it moving blood? If it thinks it's moving blood, it will display a color based on the value of the mean Doppler shift and also the direction of flow relative to the probe. If, on the other hand, it decides that it's tissue, then it will display grayscale information instead, and it won't display color. So this is the basic idea, that the machine has a little bit of information from just 8 transmit pulses for each sample volume. It calculates those 3 parameters, decides whether it's tissue or blood. If it's blood, it displays the color that's calculated based on Doppler shift and flow direction. Here's an expanded view of the color bar. In this case, the baseline is in the center, but it needn't be. The baseline can be shifted up and down, just exactly the same as the spectral display. The upper and lower limits are the Nyquist limits, again, just as the same as for the spectral display. Notice in this case the Nyquist limits, which are still 1/2 of the Doppler PRF, but they're labelled on the display in centimetres per second. We haven't done any angle correction, so how is the machine calculating this? Once again, as I explained for pulse Doppler, if you have an angle corrected, the machine will assume that an angle is 0. In other words, the beam is parallel to flow direction. The other thing I want you to notice is on the left-hand side there's a grayscale bar, and there's a green line on that at one particular level, and I've labelled that the grayscale threshold. That's an important value in the machine's determination of whether each point is soft tissue or blood. The machine sets that threshold value. You can change it, but I would suggest that you normally wouldn't do that because the preset is normally very appropriate. So what controls do you have? Well, you have to set the color box position and its size and the steering angle of the beam, at least for linear probes. You have control over the velocity scale, so you can increase and decrease the velocity scale just as you can in pulse Doppler, and this is going to change the range of velocities or Doppler shift values that can be accurately displayed. You can shift the baseline, as I mentioned earlier. You have a gain control, and this is very important because what we're going to see in a moment is that Colour Doppler is not as good at detecting flow as pulse Doppler. And this is simply because it has less information to work with. And so optimizing the gain in order to detect any blood flow that is really present is very important. A technique that people often use is to turn the gain too high until some of the colour begins to spill outside of the real flow channel, whether it be a blood vessel or something in the heart. So the blood flow is being displayed in areas that are actually tissue. And then you reduce the gain again, so you turn it too high and then back it down until the flow is just constrained within the area where it should be. And you know then that you've maximized the gain subject to allowing the tissue-blood discrimination function to work properly. And finally, there is a wall filter, as I mentioned, in Colour Doppler, as there is in spectral and continuous wave Doppler for the same reason. And you can change the setting of that if you need to. One of the things that it's important to understand is the limitations of Colour Doppler when you compare it with pulse Doppler. So there is no audible Doppler signal. There's no Doppler signal you can listen to. There is no spectral display. So you don't have the usual tools that you're familiar with from the other kinds of Doppler. There are no velocity measurements. The wall filtering is not as good in Colour Doppler as it is in pulse Doppler because, again, of the small amount of data that the machine has to work with. Similarly, for the same reason, the determination of the Doppler shift is less accurate and more variable. So you'll see variability of the colour just simply due to the fact that the machine is working with the smallest amount of data it can get away with. And then finally, Colour Doppler is particularly poor at detecting slow-moving flow. So that's its kind of weakest point, is the ability to detect slow flow. One of the things this means is that when you are looking for slow flow, for example, if you're looking for a trickle of flow in a vessel that is 99% occluded or perhaps thrombosed, then you would want to make sure that you set the Doppler controls and the velocity scale so that you maximize its ability to detect slow-moving flow. If you move from looking at an artery to looking at a vein, you will readjust the velocity scale when you move to the vein to a lower setting so that you will detect the slower moving flow in the vein. So optimization of the controls is particularly important in Colour Doppler because of these limitations. I mentioned before the variance, which is one of the parameters Colour Doppler measures. Normally, this is used just internally within the machine to help it determine whether each point is tissue or blood. However, there are times when the variance is actually displayed as part of the colour display, and this is an example of that. Notice, by the way, that the typical convention that's followed with the red and blue colours used to represent the Doppler shift is shown here. Red is above the line, so red corresponds to flow towards the probe. Blue is below the line. That means flow away from the probe. But just be warned that it's perfectly possible to invert that and to flip it so that then the role of the colours is reversed. But in this case, what I want you to notice is that there is a green colour added into the image as well. So we have the red and blue, and then we have this green colour displayed in areas where the variance is abnormally high. So if you think about what the variance is, it's measuring the range of Doppler shift values in each sample volume. If we have a large variance, that means there's a wide range of Doppler shifts. We refer to that as spectral broadening, and it's one of the classic signs of disturbed or turbulent flow. So this green display is highlighting areas where the blood flow is not smooth, but rather it is disturbed and perhaps completely chaotic and turbulent. This only occurs in the presence of pathology. So it's a very good indicator of severely abnormal flow caused by the presence of disease. This is not normally turned on, except in echocardiography, where it has this particular role of highlighting areas of disturbed and turbulent flow. Now here's another application of Colour Doppler that's quite different. You can use it to look at the distribution of blood vessels within a soft tissue organ or region. In this case, we're looking at a thyroid gland, and we're looking at the distribution of arteries and veins within that gland. You may be doing this to look at the function of the organ itself, or you may be looking at a mass and the region around that mass to determine if it may be malignant. So this can be a very valuable application of Colour Doppler. Now what you can see here is that this image is difficult to make sense of. We have a jumbled mixture of reds and blues because we have a variety of arteries and veins with all sorts of different orientations relative to the ultrasound beam, and therefore it's difficult to really make sense of this image. Take a look at this in contrast. We have a completely different mode of Colour Doppler being used called power mode, or amplitude mode it's sometimes called. Now the reds and blues have been taken away, and we're simply looking at a scale that goes from black, orange, red, all the way to yellow, and that simply indicates the strength of the Doppler signal at each point. So we're simply looking at the presence of flow. We're ignoring direction and Doppler shift and simply saying, whereabouts is there flowing blood? You'll see how much easier this is to interpret, how much more meaningful this display is. So this power mode Colour Doppler is very useful in specific applications such as this. The machine is displaying the strength of the Doppler signal, the Doppler power, not the Doppler shift. It's a simpler display, and it is ideal for the application I've just shown you of looking at the vascularity of a tissue region. Now, there are a couple of benefits that are perhaps unexpected when this was first developed. It's more sensitive than conventional Colour Doppler, so you can detect weaker signals and display them with power mode. Another advantage is that, surprisingly, power mode Colour Doppler will display flow even when the beam is at 90 degrees to the direction of flow. Now, why is this? The mean Doppler shift is indeed 0 when the angle is 90 degrees. This means conventional Colour Doppler won't see that flow. However, there's an artifact. That means there is a Doppler signal present, but it's an artifact signal. Of course, the machine doesn't know this, it simply knows there is Doppler signal, and so it displays it. So thanks to that artifact, power mode Colour Doppler will see flow even when it's at 90 degrees. So power mode is a very good modality to use when you're looking for vascularity or when you're wanting to detect very weak flow. Here's another example. There's a vessel that's almost totally occluded with just a little thread of flow still present. And of course, this can be, from a clinical point of view, a very important finding. So power mode is definitely the ideal mode to use in this particular case. So in summary, Colour Doppler is based on the same general principle as pulse Doppler. So there are pulse and echoes, range gates, etc. And there's even the wall filter. So in many ways, it is just the same as pulse Doppler. But because it has to detect the Doppler shift at hundreds of points in a fraction of a second, there are all sorts of shortcuts. Colour Doppler is excellent as a pathfinder, getting an overview of the blood vessels in a region, the way they relate to one another, their interconnections, but also the way they relate to organs. So Colour Doppler is excellent in this way. It can highlight areas that may be abnormal. If an area has a very different appearance in Colour Doppler with no obvious explanation as to why, it may be that there is disease at that point, and you would investigate it using pulse Doppler with a spectral display. It's not quantitative, it's important that it be optimized, and for all of these reasons, it's very nicely complementary to pulse Doppler.